Hello. How are we all doing today? Is that a good thing or a bad thing? If it is self-driven because you're having fun, I'd say that's a good thing. If it's because I've assigned you too much work, that's a bad thing. I think this, oh, that's very loud. I think this Windows update's kind of a blessing in disguise. So it broke all of my audio and my streaming stuff, but now I can play games full screen. I see. Yeah, I would try to pace yourself if you can. Make sure you leverage your teammates. It should be an achievable project for the semester, not necessarily one person's efforts, but I can see the danger of that. Yeah. No, we need a highlighted mouse. Here we go. Any excitement for Repentance coming out, or am I one of the few for that? I think it's 2 days. Let's see. Let's see. Let's see. March 31st. Why are you here? Okay. There we go. Thank you, Classic Shell. Okay. So, where are we at with class here? So, anybody having any headaches with the homework at all? Everything going okay with that? Because we have until April 2nd, which is Friday. Kind of gave you longer than normal for this one in particular. I know we have the 1st as a break day, and I could have either done it before or after the break day, and I didn't want to cut you short. I felt kind of bad about assigning it after the 1st, since I know that's a day off, but kind of gave you extra time to hopefully help out with that. But I suppose let me know if you're running into any issues with the homework, either email or chat or drop by the office hours. So, other than that, I assume we're okay. Let's continue on then with some UML. So last time we finished up project model or project planning, project modeling, right? We talked about Kokomo and EVA, and just to kind of wrap that up in a neat little package for the exam when, we get to that point. I'm not going to make you do anything complicated. Like if I want you to run a Kokomo model, I'll give you all the numbers in the equations. You don't have to memorize them or look them up. I'll give them to you. I'll probably be more apt to give you questions about why you would use a model. So why would you use embedded over organic, or why would you do advanced over basic? More of a let's think about why we would use this thing. Might give you a little bit of math to do, but again, I'll give you everything you need. I'm not expecting you to memorize an empirical model that's I kind of intentionally simplified for discussion since it's basically just a big Excel spreadsheet or, a C++ program or something like that. But what we're going into now is UML. So we talked a little bit last time about modeling, about why we do it, and I hopefully convinced you that it can be useful. Don't let the cynical and jaded people in industry tell you that it's absolutely worthless. You will run into that at some point. It can be helpful, right? And it's for communication purposes and clearing things up. And we discussed last time that there's really two categories, structural and behavioral. And today we're going to start off with structural when we get to class diagrams. Off the screen, please. And I guess this is going to be a pull it off of Twitch Day since, yet again, I forgot to hit record, but at least we have that option. Okay, so we ended right about here, I believe. So we talked about visualizing, so showing what the system does, specifying it, developing templates. Again, we can auto-generate code or we can use it to directly build everything. Also used for documentation, very important. Always document. So let's start with new stuff rather than rehashing old stuff. So UML is actually a formal specification. So there is a versioning system in place for UML. We're currently at UML 2X, I think. Let me pull open, all the things that you think you want to have open for class, and then you forget. UML, we are at version, which version are we at? Thank you for that. Yes, I love specifications. Here we go. They updated the website 2.5.1. Okay. So December 2017 was the last update for UML. So again, this is a formal language. This is something that we can look to if we want to, say, develop tools and develop approaches that leverage the standard. And that's kind of why I have you all really focus on some of the syntax. And there's a little bit of flexibility, obviously, with homework assignments and with exams and all that, because I'm not expecting you to be UML experts at this point, but we should at least, make an effort to try to follow the syntax. So UML started out of research projects, which a lot of these software engineering things seem to do. And this was done by 3 different people. So basically 3 different researchers spread globally. So there was, in the 80s, the Booch method, the OMT method, and the OOSE method. three different guys working on very similar topics. This kind of happens often in research where there'll be some topic that becomes really interesting to work on. And, like any research, people will kind of go towards this topic and try to make headway with it. Well, these three actually decided to work together, which is very, not strange, but not common to kind of group up together and actually come up with a, you know, formal standard out of it. It has happened, but people tend to work in their own little university silos more or less. And the fact that this actually came out and became a specification, at least to me, is fairly impressive. So it's at uml.org. That's where we were just at. But these are the three guys that did it. This guy has very long and crazy hair now, so very professor-like. I'm doing my best, but can't get beyond the short haircut. So what is UML? Let's kind of break down why it is what it is. So the nice thing about UML is that it's process independent, meaning we don't care which software process model you're following. You can be doing waterfall, you can be doing agile, you can be doing prototyping or spiral. It doesn't matter. UML will work for all of them. And that's kind of nice because now we have this modeling technique, which if you're an agile person and you want to talk to a waterfall person, you can still speak the same language. Right? That's going to be a lot of very positive forward progress that you can make if you're, say, trying to mesh together two projects. Maybe one's a more legacy project, one's a new and exciting project. You're trying to mesh things together, and hey, we have UML models describing everything we've done. Okay, well, we can all very easily understand what's going on. Or if we have any tools that rely on the models that are generated, they will be able to work with those too. But UML tends to be very good at use case driven processes or iterative or incremental, basically any kind of a process where we are kind of making little chunks of progress as we go. It still will work for something like Agile where it's very flexible and freeform too. But UML tends to be kind of a iterative process. So let's start with the use case model. Now let's iterate it into a class diagram. Now let's iterate that into an object diagram. Now let's talk about a communications diagram and a behavioral diagram. So we're kind of going through the different models that you will all know very soon and kind of expanding on purposes of features and getting more details. And it's you can kind of see how iterative is. I'm doing this so like it makes sense to you, but you're kind of refining things as you go. Interestingly, we can use UML for other projects too. You don't have to necessarily use it for software. If you're doing some kind of an electrical engineering project, you're doing some kind of a maker project where you're building a 3D printed robot at home. You're buying motors off of Amazon or, any of the electronics websites on the internet, like DigiKey or whatnot, just throwing names out. You can model these things out too, right? What's a use case of a 3D printed home robot? Well, maybe we want to follow a line. Maybe we want to go to the corner. Maybe we're developing pathfinding algorithms with sensors. We can derive use cases for them. Maybe you don't take it down to the programming level, but you can still see what the interactions are with the systems, right? We also have high-level diagrams, like architecture diagrams, how everything fits together and interacts with each other. So basically, it's a very independent language, and it can be very, very powerful. So the building blocks of UML has a few, UML has a few building blocks. We have things, we have relationships, and we have diagrams. So the things, not an official term, this is the object that you are modeling. This is the first class citizen. In the object diagram, it is the object that you are instantiating. In a class diagram, it is the class. In the sequence diagram, it's the processes and basically what those are defined to be. It's a thing, basically, the purpose of the model. We've got relationships too, and that's how everything works together. So class diagrams, we have relationships, we have aggregations, compositions, probably some of those horrible terms that you might remember from Intro to Java. But we have decompositions, we have message passing for behavioral and process models. Basically how systems talk to each other. We'll model that. And then we have the diagram, which is the graphical version of how we lump these two together. So in our current version of UML, we have two different types of diagrams, structural and behavioral. And I've kind of beaten this to death already, so please feel free to stop me if I'm going too fast, but structural is the static side of the system. Behavioral is the dynamic. Structure is how things are put together, it's how things are related to each other, and it's how we can basically construct a system. Right? If I give you all a class diagram of a C# web application that talks to an SQL Server database, it's got a front end, it's got a back end, and we have all these different pages for user interaction, stuff like that. And I break it out into classes, and I give you a structural diagram for that, a class diagram. You could all probably implement it. Maybe you need some front-loaded time to figure out C# and SQL Server and all that, but you're going to know how to build a class, right? Might look different, but that's not specified in the class diagram. I'm giving you attributes and methods and classes and who's related to who. You can all do that without, really understanding a lot of the requirements. The behavioral diagrams on the other side is how things kind of work while it's alive, so behaviors. If you instantiate class A and then you run function login, the behavior is that we reach out to the database, we pull the user information, we get the encrypted password, then we encrypt what the user input into the password field, compare them, do we allow login, yes or no? That kind of a thing. Like what are the sequences of events that have to happen? Or what are the messages being passed from class A to class B? So static, dynamic. All right, here is the kind of UML high-level hierarchy of diagrams that we have. So here you see structural and behavioral diagrams. Over here, class diagrams, component, object, composite, deployment, lots of different diagram types. Same over here with behavioral. Use cases, hopefully should be well familiar with at this point. Activity diagrams, interactions, state machines, timing, sequence. All of these diagrams, we can pretty much understand their purpose just by the name of them, more or less. Right? Deployment, we are taking some kind of a project and actually deploying it onto real world hardware and seeing, what it does. So what are the real world concerns at this point? We are not going to go into every single one of these, but we're going to go into a handful of them. So class diagrams, object, use cases, sequence communication, those are pretty much the ones that we are going to be digging into. Nothing stopping you from picking up the other ones and using them if you need them. Like for me, out of all of these, state machine diagrams are probably some of the more helpful, if you wanted to go above and beyond, because then you get an appreciation for, the different states your software can be in. Are we at the main menu? Are we at gameplay? Are we at options menu? Are we at boss fight? Or is your embedded system off, booting up, running, accepting input? So it can be helpful for that. But you can also kind of infer states from some of these other diagrams too. There does tend to be some overlap with them. All right, questions so far at all? Are we all good? Everybody okay so far? Today's a big info dump, by the way, so not a whole lot of stop and think about it type questions, but please feel free to stop me if you want more detail. Happy to talk about this. And once. I love springtime in Michigan, even though it's, I think, 25 degrees out, Fahrenheit. So relationships are one of the first things that we'll talk about here, and we're going to start off with class diagrams, just to kind of ease you into this. But what is a relationship but a connection between two different, again, things? And thing is kind of a nebulous term here. It's a class, it's an object, it's a use case, right? Thing is a fluid term. In UML, a relationship is a path, which just means that it's a line between two things. But we do have different types of lines in UML. So this is, again, going back to the syntax of the model. We have filled arrows, we have open arrows, we have dashed lines, solid lines, diamonds, filled in diamonds. Basically, they all mean something for UML. And if you are going to be going down the path of UML, you're going to have to really pick up on, the specific syntax. So what do we have? Dependencies, generalizations, associations, realizations. We're going to talk about all of these here in a few moments, but basically we're really describing what relationship one object has to another, right? Is it a class that is made up of a bunch of subclasses? Is it basically like an inheritance or an importing thing where for this class to be instantiated, I need, function calls from this class to be satisfied. So we can really realize this graphically and very quickly, kind of show other people the purposes of all of these classes that we're building up in our system. So we're going to start with class diagrams. So it should look familiar to you all. My understanding is that you have, been forced to see class diagrams in your recent past. But what's a class diagram but the makeup of a program, right? This kind of fits very nicely in with Java since kind of object-oriented by default. But you can still use this for C and Python, pretty much any language where we can encapsulate features. So just as a bit of a refresher, here's our class, right? Here's the class name at the top. Usually the first half are the attributes, so your variables for the class. We can specify if they're public or private or protected, so what's the visibility of them. And then we have the methods or the functions that this class would run, right? So we have a nice encapsulated thing. This is our thing for class diagrams. Our relationships are going to be the lines in between them. And you're going to kind of notice that some UML drawing softwares will kind of draw things, maybe a little bit differently at times. Just something to kind of be aware of. Again, for us in class, using Visio or Draw.io is fine, right? All we need is that nice vector drawing so that we can move things around. But if you go down the Eclipse plugin routes, it's going to look a little bit different. And I'm pretty sure I've got some of the tools in Blackboard for you all for the different UML drawing. I know I put it up there for use cases, but like if you get a plugin for Eclipse, it might look slightly different than, say, a plugin for IntelliJ or Draw.io or Visio or something like that. Mainly in just like the weights of the arrows and the, do we have nice straight lines or elbowed lines? The little extra fluff might look different. Just a warning. But okay, so let's take a look at this diagram and break it down then. So we have basically a class diagram describing a course at a university, right? So we have a student, you have personal information, you have a student number, your email address, and we're trying to figure out, can you take a seminar class or not? And seminars are special types of classes, right, where it's usually either research the professor is interested in, or it's like a group of students getting together and kind of self-organizing around a topic. I don't know that this is actually an option at Grand Valley, but it is one thing that has been done in the past anyway. So we have student classes, a professor class, seminar class, and an enrollment class. And you could replace seminar with course, right? It could be just CIS350. So you might have an enrollment class as well here, where this could be tied to your seminar, right? So your information, you'll have maybe an enrollment record, which could just be a class. with your marks for the semester, your grades. What's your average to date? What's your final grade? Um, we have some other information here. And again, I'm not really trying to break down what this exact class diagram is doing. We care more about the actual syntax of it. So a student can be enrolled in an enrollment. The enrollment can be tied to a seminar. A seminar can be tied to a professor. And we have some little, kind of syntactic sugar, I think is one of the terms here, where this relationship between student and enrollment, we don't necessarily need this enrolled tag on here, but it tells us what the purpose of this relationship is. For instance, here, if we go professor to seminar, we could have 0 to 1 professors running a seminar, right? So in theory, if we're running a class where there's no professor, I don't need to be here. Maybe it's a flipped classroom, so the Chen method is used for more than just database. I am honestly not familiar with the Chen method. I feel like I should be familiar with it. Can you give me a quick 2-second overview? Oh, it's a notation model. ERD. Gotcha. Okay, sorry. My database ERD or ER knowledge is not as strong as it needs to be. Yeah, Chen ERD notation model. Okay. 0 to 1 to many. Interesting. So as far as I'm aware, this is just a part of UML. So I didn't realize this was particularly related to Chen. Let me look that up offline because I wasn't familiar with it, honestly. So to me, understanding that it's an ER diagram, okay. I mean, I do know that this does look like a database, like an ER diagram kind of thing, but the attributes and the labels, this is just straight up UML. So this is part of the standard. But I mean, I'll look into it and let you guys know. That's interesting for me to learn. Um, yeah, so good points. So yeah, if you're familiar with a different approach, then this should be hopefully pretty easy to parse out. So 0 to 1 instantiations of this class can be tied to 0 or more of this class, basically. Um, and if we have a seminar, we could have 0 to many, and we could have 0 to many students. So basically, if I've got no seminar and no students, this diagram will still hold. If I have one seminar and 0 students, it will hold. If I have one seminar and 20 students, well, I can actually say that the list of students that we have are in a waiting list to get in. And maybe we could order them by registration date. You don't get that information necessarily here other than first in, first out. But, we can kind of understand what's going on here if we were to build out the system. So, we have class diagrams. All right, you should hopefully remember this from Java 1. We started out with use case diagrams, right? Kind of the high level goals of our system. We talked about that verb noun syntax for constructing what the purpose of our system is. Well, if we look at our use case diagrams, and we follow the noun verb or the verb noun syntax, right? Like load map, start game, draw visualizer, whatever we're doing here. The noun could be a class. The verb could be methods. And this isn't the end all be all definition, right? You have to, sit down and think about it. But this could be a reasonable starting point. So if we have, say, a use case for, what's a good one? So let's say that we are defining a use case diagram for a seminar. And we have use cases for add student, drop student, create seminar, and we have like the actors would be the students and the professors and maybe the system behind the scenes like banner, kind of tied to this. Well, add student, we could just say add in here, and student could be one of our classes. So you kind of get a nice starting point with use case diagrams. And this is part of that whole iterative refining nature that I talked about at the beginning, where UML kind of works for us. Now, if you have this rough outline based on your use case diagram, you might not have everything you need, excuse me, to develop a full model, but we can refine it over time. So let's start out with just our classes. Okay, we are adding students into our system. Or maybe let's pick a game. What's your Chen notation? This was all about a MMO type of game I noticed here. So we have character. Okay, so character is going to have a level, a character name, hit points, mana, um, type, all this kind of fun stuff. Well, we're going to define a character class. Character would have all those attributes, and then we're going to list out all the operations that a player can do. They can move, they can attack, they can pick up item, interact with NPC, update location to server, and then we can start adding in relationships. So player is tied to database, player is tied to game manager, player is tied to other players. But we can iterate this is kind of the key takeaway. And you would check in a class diagram and a use case diagram, all these diagrams you would put under revision control. Right, version 1 is just the rough outline. Version 2 added relationships. Version 3 finalized X class. So basically we're just kind of building up how we're going to construct our system. And again, if you do a good job specifying this, you could, in theory, I say in theory because it's dependent on the tool set, you could plug this in to, an Eclipse plugin or an IntelliJ plugin and have it spit out function stubs and class stubs for you so that let's say that I drop this into a plugin here, and assuming that the syntax is understood by the plugin, public class student, public string name, public string address, public string phone number. Maybe it doesn't quite understand exactly what you wanted, and you have to go in and fix things, instantiate what get seminars taken actually means. But all of the boring boilerplate code just got automatically created for you, including relationships. So maybe enrollment extends seminar. That relationship is kind of implied by these relationships that we're defining. So basically the key takeaway is that this can be very powerful for you, especially if you're not ready to just go right into coding. So now we're going to start talking about some of these relationships, and it's going to get, kind of hopefully not too deep for you all, but, enough that we can understand the purpose of them. So like I mentioned, all of these object drawing types have meaning. Relationships is really where you start to see it kind of subtly be important. And I say subtly because if you're looking at a figure and you don't notice the dashed line, or you don't notice that it's a solid line, one means something, another means something. So first things first, let's start off with a dependency. So this is your uses relationship. Basically, we are kind of including something in another class. So let's say in this case, A is using B. A might be, directly using something from B, but B is not really impacted by A, if that makes sense. So if this is class, it's a good example. Let's go back to this one. Class student, class seminar. If I change my student name, and we see kind of, it's not a dashed line, but if this were a dashed line, the seminar needs a list of students to add and to drop, right? But if I change my student average mark, that's not going to impact the seminar in the least. Whereas if I change the, something on the seminar side, like I change the fees to register for a seminar, that's going to directly impact a student because you have to pay to register for the seminar. ham-fisted example, but basically it's like a one-way relationship is kind of what I'm trying to get here. So one of these, types of behaviors is what you'll see. So if A uses B, um, we might have a local variable type B inside of A. Maybe B is a return type, maybe it's a parameter, maybe A is just calling B's methods. So if B is your game manager for our MMO, B dot randomize game world, maybe A is your overall game construct or something like that. Or local game state equals B dot get game state. Basically, hopefully you can kind of see here that we're just using things in B. We're not directly interacting with it or importing it. We're just kind of using that. And that is dashed line with arrow, or a directed path, I suppose, with the arrow. The next one we have is the generalization. So key things here, solid line, hollow, triangle. Basically, this is, it's kind of like the is a relationship, and we're going to have is a, has a. This is kind of how we describe some of these relationships. Think of it like a superclass type of situation, or a parent and a child class. So B is a, which is kind of hard to say. Basically, it's like you have a general superclass, which superclass is just some kind of a larger construct that you're going to kind of aggregate smaller classes from. So if B, the canonical, getting tripped up here in words. The canonical example for something like this is animals or cars or things like that. So if A is an animal, B would be a dog or a cat or a tiger or a liger. To go back to 90s, 2000s era references. Basically, it's a form of inheritance, and this is the subclass, this is the parent class, superclass, subclass, whatever you want to call it. Basically, we're kind of inheriting things from A into B. So hopefully that made sense. It will become clear, and we do some examples too. Another example would be A is a vehicle. B could be a car, a truck, a plane, a submarine. We're going to use generic methods and attributes out of A to specify, increase velocity, turn left, turn right, drive forward, drive in reverse, if we're a vehicle. What does that mean for, dune buggy, there we go, relevant to Michigan. But it would be up to B to implement that specific to its type. So if this is vehicle and the goal is to turn left, dune buggy, we'll use your example, turn steering wheel left, right? But if it's a submarine, you have to turn the rudder the opposite way, and then, turn off one propeller, turn on another propeller. Dated knowledge of 1950s era World War II movies and what submarines actually do. Right, basically we're going to have specific instantiations. Dotted line means we use some, solid line indicates what we're building. That's kind of a good take on this. It's going to be specific to it too. So here we have another one. So this is an association with no direction. So kind of just the key is to really understand, various lines have arrows. It'll become pretty clear. We don't have all that many, honestly. So we have arrows and we have diamonds, and you may see associations where they are directed and where they're not directed. I'm just trying to generalize in my head, and I think that's probably a good way to look at it, what you got there. Okay, so generalization, basically inheritance. Association means that we are just somehow connected to another thing. So there, in this particular example, there is no directed line, right? A is not interacting with B specifically. A and B can talk to each other. There is some sort of interaction here, basically. And typically, if you're going to do something like this, and honestly, with any of these, you'd probably add some extra syntax, some extra adornments onto the line to really tell what the relationship is. Like here, it's all blank, right? And it's kind of hard to understand what B and A are doing here. If we go back to the example, here we have a straight up association between a professor and a seminar. So by itself, this line doesn't tell us anything other than a professor and a seminar are linked up together. But when we start adding on, say multiplicities here, so there is 0 to 1 professors, there are 0 to any seminars. Okay, so now we know how many of these objects will be instantiated. We also know that a professor will instruct a seminar, right? Just kind of based on how we can read this. And there's usually you would put the adornment closer to the actual object. Right here, it's kind of implied. It's not like specifically that this goes right here. But reading this, we can kind of understand, using a little bit of hopefully common sense that the seminar is not instructing the professor, I guess, unless it's student run, in which case everything's out the window. But basically, kind of the key is that when we're adding on these relationships, adding information's key to understanding its purpose. And this is more for you, the programmer, in a way. So we have just an association of some kind. Typically add on multiplicities, how many of each object. We can add directions as well. So here we have a directional relationship, a directional association, sorry. Basically, in this case, we have some aspect of B in A. So in this case, it's very particular that we are including something from B in A, whereas before, over here, we're just using something. So yeah, your example, Borimako, works out perfectly, I think. So in this case, we had class A and class B. There would be like a private B variable in here or something like that. So with these relationships, I also talked about multiplicities. And if you're not familiar with the syntax or with what a multiplicity is, basically you're specifying how many of thing exist. And I'm saying thing because this will apply to any type of UML diagram. Or I guess ER diagram if we're leaving UML. But here we have, there's only one department, there's only one boss. So if you have a single number in here, that is exactly how many of this object will exist. Right, so in this case, we have a very tiny company with only one department, meaning we only have one boss. All right, well, we may only have, so this is now a HR example, by the way. We may have one employee, but an employee can have 0 or more children. Right, so 0 ... asterisk means 0 to any. Any's, asterisks are a typical wildcard character. You could have 0 to 2, you could have 1 to 5. It just, not children, obviously, but, well, you could have that. In terms of the multiplicity, you're basically defining a range of some kind. Maybe we can have 1 to 5 departments, and each department only gets one boss or something like that. In this case, we could have one boss responsible for 1 or more employees. And again, here we're just showing multiplicities, but we're not saying what these associations are actually doing in this example. Now we could break out with a little unofficial explanation like you saw back here, where we have this little breakout to a kind of a notepad-y type thing. But we can kind of get a feel for what our classes are going to be doing once we instantiate them. All right, so we have our dependency relationships, we have our inheritance relationships, our association relationships, and now we're going to get into the fun ones, and this is where it can get mildly confusing. Honestly, the other ones are pretty straightforward. So the takeaway from before, they will interact in some way. Solid line, we are bringing in an attribute or a method into a class. The dashed line for the dependency, we're just using something. The empty triangle or the empty arrowhead is an inheritance relationship, superclass or subclass relationship. Now we're going to get into the aggregation and composition ones. And these ones just, they're not hard, but they just take a little bit of thinking, honestly. So this is where you see the diamonds in your class diagrams. If it is a solid with a open diamond, it's going to be an aggregation. If it's filled, it's a composition. And again, we're just telling you how classes relate to each other. So if we're aggregating, we have a has a relationship. So basically, let me go to the example first because this is going to be easier to talk about, I suppose. Both of these are going to be the same thing. So has a, or is a kind of, or is a part of. These are what aggregation and composition mean. Okay. So the example in general, a cardinal is a kind of bird. A truck is a kind of land vehicle. MMO is a kind of game. 2D is a kind of graphics drawing. 3D is a kind of graphics drawing, right? So we basically just are saying how we are forming a big thing from smaller pieces. Aggregation is the logical side, composition is the physical side. And I'm going to go back a slide to explain what that means. So if we have an instance of a car or a vehicle for, not for instance, if we're defining what a vehicle is, okay? A vehicle can have doors and wheels and all these different parts. The entire thing is the aggregation or the composition. It's the big superclass, right? If we have a wheel and we instantiate that, it can be part of a vehicle instance. In general, okay? When we're composing, and let's say that we instantiate a door, it's only ever part of one specific instance. So in aggregation, we can have a wheel be part of any vehicle that has wheels. Composition, we are only part of a single specific instance. And what this means is that aggregation, when let's say that we instantiate a wheel class, and we'll just use wheel for both of these because wheel to door might be confusing. If I instantiate a wheel and I now instantiate a car, and let's say that I destroy the car object. All right, I call vehicle.destroy. The wheel still exists in memory. Okay, it is just a generic wheel object that we have created. By aggregating, we are saying the relationship is that we are not directly tied to a particular instantiation in memory. Yes, it is an object that we have, that we're holding in memory, but I could extend this, copy this wheel for 500 million vehicles. Let's pretend we're doing a production line of Ford Tauruses or Tauri or whatever that's going to be. I instantiate a wheel, I can then start copying it, and aggregation, if I destroy the actual vehicle object, these wheels will still exist. So there's no linkage between the whole and its parts. Composition, on the other hand, let's say we have this vehicle, and I call vehicle.destroy. That vehicle will then go through and destroy all of its parts to free up that memory, right? Does this hopefully make sense more or less? So if we have B is composed of A here, or wheel is part of vehicle, door is part of vehicle. When we destroy this vehicle memory object, wheel still exists if it's aggregation, wheel would not exist if it's composition. I know I'm really kind of talking in circles here. Basically, it's a relationship of who is in charge of the memory of the object. So here's another example here. So again, aggregation is the open diamond, composition is the filled diamond. If I were to say, create a program that defines a school here, right? So we have a school, students, departments, courses, instructors. If I were to say, close down the school, okay, so our school is shutting down. The students will still continue to exist regardless if the school is there or not, right? So you, as people, will still continue to exist if GVU shuts down, GVSU shuts down. However, the departments would no longer exist because they are a composition of the school. Or sorry, the school is composed of departments. Students can be a part of the school, but you're not tied to the school. Aggregation can be extended by anything, and composition only has one specific extension. Again, it's extension, I can see where you would use that word. It's basically our relationship here. So maybe to hopefully contextualize this slightly differently, you're trying to build a big object of many pieces. And that's kind of why I'm using vehicle and using school. Let's see, what do I have here on my desk? Kleenex box, perfect. I have this Kleenex box. It's beautiful. It's got a bunch of Kleenexes in here, and I don't want to start ripping them out because then I'd be out of Kleenex. But if this is an aggregation relationship and I start flinging Kleenexes around the room, they will still exist, even if I get rid of this box. If I'm saying this is a composition relationship, when I destroy the box, let's say I set it on fire, all the Kleenexes inside would be destroyed as well. All it really boils down to is memory management, honestly. And this type of example, yes, exactly. But it depends on how you specify the relationship, right? So you could say the exact same thing about a door, right? You can have 500 doors, and if they're an aggregation relationship, they would still exist. But once you call them a composition, then they're directly tied to one specific vehicle, I suppose. So this is one of the arguments in UML where it can be unnecessarily confusing. And I'm not saying this concept is hard, right? If it's explained properly, it makes perfect sense, but it's needlessly complex. So this is one thing where it's actually kind of considered something called syntactic sugar, where it's just unnecessarily complicated. A lot of people don't like this relationship. They just rather it be a general form. So the other example here is let's take birds, right? So we have eagles, we have cardinals, we have finches. These are all different types of bird. If we say all these different subclasses are compositions and we destroy class bird, all of those specific object types would also go away. But if they're aggregations, they would all still exist if we get rid of class bird. And again, this is an in-memory at runtime type of relationship here. Maybe you are doing duck hunt, I don't know, and you kill all the ducks that are on screen, so you call bird.destroy, and that gets rid of all the birds that you have in memory. We'll continue on with this next time, but I think you're kind of getting there at least. The key here is that we just have a whole bunch of different types of relationships. You can take a door off the car to salvage it, or you can take some explosive to the entire car. That is exactly right. That is a wonderful example. Yep, yep. Taking it off would be aggregation. Blowing it up would be composition. Perfect. And we specify it with a filled-in diamond or an open diamond. Yep, there you go. All right, I will see you all next time. We'll pick up with some more examples, and then we'll get into class diagrams and object diagrams. So, have a wonderful Monday, and I will see you all next time. I'm gonna have to remember that explosive example for the fall when I do this class again. I like that. Alright, bye everybody. You too. Thanks for all the questions. And that ER diagram, I'm gonna have to dig into that as well. Yes. Oh, we have our mood music on, sure. Can you show us the egg picture? Yes. This one? Like the full picture, you mean, or? Wait, this works. There we go. Yeah, okay. Have a great day. Bye, everybody.